Hello, we're back again there, folks. We're still at it here. The next thing that we're going to talk about, before we get into the algebra of these vectors in 3 dimensions, which will again feel more familiar to us, I want to mention that if I take any two of these vectors in 3 dimensions, because we know that the three of them are not coplanar, the three of them are linearly independent. The three of them form a basis for space. That if I take any two of them basically define a plane. They become a basis for their plane. So the easy one to talk about are W and V here. We can see that they sort of define this plane, that if this model was sitting on your desk, it would be the plane that your desk is sitting on. In this case, it's actually the XY plane, because we defined this to be the x-axis and this to be the y-axis. This would be the XY plane, but the way I've got this held, it's kind of tilted. It goes off in any direction. What we're going to do now is, because it's hard to picture the plane that would be defined by, say, U and V. This one was easy because it sits on a piece of paper, but what's the plane defined, the basis, that U and V are a basis for that plane? And so what you're going to do is you're going to get your stickies and put them across U and fold them so they're sticking out of U. All right, and I'll show you that in a second. I'm going to pause the video and do that myself. Okay, so you can see I've attached my stickies there. Now, what's weird is, this vector U, the sticky I can move, and there's an infinite number of planes, so that piece of paper represents a plane sticking out that. But the thing is there's also one for V that I got, and if I lay them nicely, I should be able to picture the plane. I should be able to picture the plane that both U and V are on at the same time. It's hard because my hand's in the way, but hopefully you can see this with your model. Any two linearly independent vectors in space form a spanning set for their plane. And so U and V in this case for the plane defined by the two sticky notes. Now remember, the planes sort of go on forever and define a two-dimensional piece of paper in all directions forever. So these are infinitely large sticky notes that we're talking about, but you get the idea. That I hope that they define that plane where the two sticky notes sort of come together and form a plane. And I could have tried the same thing for W and U, but it would be starting to get a little crazy. So if you would like to try that, you're welcome to. What does this mean as far as a note is concerned? And this goes back on your piece of paper, not on your note, but on your three-dimensional model. For any two non-collinear vectors, V and W, in space, they are a spanning set for their plane. Right? They give all the information for the plane that they exist in, because they're non-collinear, which means they're non-parallel, which means they're linearly independent, which means they're a basis for the plane. And then other vectors in the plane can be written as a linear combination of those. Notice that since I'm talking about the two of them, I'm talking about the plane. The third one that we're missing, so in this case I was talking about V and W, I couldn't consider U as a linear combination of V and W because U doesn't exist in that plane. It's a different plane. So this time I'm collecting up any two vectors in space that aren't parallel, and it defines a basis. It defines a plane that they exist in. All right. Next and last video, we will go through some algebra of spanning sets in 3 dimensions.